Welcome to this section on search cursors. In this video we will give a brief overview of what the search cursor is, and in the next video we will go into more depth as we go through the Esri documentation for the search cursor. So what exactly is an ArcPy SearchCursor? It is an iterator object that allows read-only access and sequential access to rows in a table. Read-only and sequential are important components here. We can only use the search cursor to query and read the data that is returned. We cannot manipulate the data in any way and alter the original table. The search cursor is always sequential. If we do not specify an order by with an SQL clause, the search cursor is sequential based on the object ID. Essentially, the ArcPy SearchCursor is a way to programmatically query and extract information from GIS datasets. Here we have a tabular dataset with our object ID and 3 fields. When we use ArcPy and the search cursor, we get returned a search cursor object. This search cursor object is an iterator and it allows us to move through each row one at a time. This is the sequential component of a search cursor. With the search cursor, you do not always have to return all fields and all rows. You can return a subset of fields and a subset of rows in whatever combination you desire. The search cursor is a fantastic tool for initial data exploration. The search cursor is also great for when you want to extract data from one dataset, where you can then use an InsertCursor or an UpdateCursor to manipulate rows in another dataset. In this video we described the ArcPy SearchCursor. In our next video we are going to walk through the Esri documentation, paying particular attention to the search cursor syntax and the parameters required and optional. Once we have a firm understanding of the search cursor from the documentation, we have many videos detailing the specific use of the parameters as we get to grips and master the ArcPy SearchCursor. In this video, we will walk and talk through the Esri documentation for the search cursor. In the resources for this video, there is a text file that contains the link to the documentation for the search cursor for ArcGIS Pro 3.2. Here we are in the documentation for the search cursor. If we take a look at the URL where it says latest, you can click back to 3.1 and we can see ArcGIS Pro 3.1. You could also change 3.1 to 2.9 and we can see that the 2.9 documentation has been archived and is no longer updated. We can change the 2.9 to 3.2 and this will be the latest, as we can see here in the URL. As we heard in the previous video, the search cursor is a read-only access to the records of a feature class or table. The search cursor returns an iterator of tuples. The tuples represent the records returned by the search cursor. You can either return attribute information for every field in the feature class or table, or a subset of fields. To access the geometry properties for a feature, we can use the shape at token when we supply in a list of fields as one of the parameters. As we'll see time and time again, we can iterate through the search cursor using a for loop. We will also use the Python with statement to aid in the removal of locks. And we will also see the delete statement in action in our search cursor section. Historically, the search cursor could only be constrained to match attribute criteria, but as of 3.2, you can now constrain it using spatial criteria also, as we'll see with the spatial filter parameter. Let's take a look at the syntax for the search cursor. When calling the search cursor, we actually call arcpy.da for the data access module, followed by search cursor. It would probably have been nice for Esri to have included that here, but it will be down in the examples below the syntax. There are 2 required parameters: in table, which is the feature class or table, and the field names. I'll just list through the optional parameters for now, and we're going to take a look at each parameter individually as we go down through the list of them. Optionally, we have a where clause, a spatial reference, explode to points, SQL clause, datum transformation, which can be required if setting the spatial reference, a spatial filter, spatial relationship, which can be required when using the spatial filter. The default is intersects, and search order, which only comes into play for enterprise geodatabases. Our in table can be a feature class, layer, table, or table view, and in our examples we will stick to feature class and layer. The in table is a required parameter, and the data type is listed as string. For the most part in this course, we will be using the Python window in ArcGIS Pro, where you can provide the layer name as a string. The next required parameter is the field names, and although the indication here is that it needs to be a list, if you are only interested in one field, you can supply the single field name as a string. Otherwise, it is a list of strings that represent field names. This data type here of string could be a bit misleading because, as we will see, we will be using a list object quite often. We have a description here that it is a list or tuple of field names, but for a single field you can use a string instead of a list of strings. If you want to access all fields, you can use the asterisk surrounded by string quotes. There is some advice here. For faster performance and reliable field order, it is recommended that the list of fields be narrowed to only those that are actually needed. Along with field names, we can get additional information using tokens. Let's take a look at some of the tokens. The shape at XY token returns a tuple of the feature's centroid x and y coordinates. Shape at x is a double of the feature's x coordinate, as shape at y is a double of the feature's y coordinate. We will see an example where we use shape at JSON to return the Esri JSON string representing the geometry. We will also access geometry with shape at WKT, which is the well-known text representation for Open Geospatial Consortium geometry. For the most part, we are going to use the shape at token to return a geometry object for a feature. And lastly, we will use the OID at token to return the value of the object ID field. Although the object ID field in our examples is going to be called object ID, in reality it could be FID, it could be OID, or it could be another name. The optional where clause is an SQL expression that limits the records returned. It returns a subset based on the criteria of the SQL statement. If we set the optional spatial reference parameter, the features returned by the search cursor will automatically be projected or transformed from the input's spatial reference to the one defined by the spatial reference parameter. If the spatial reference supplied in our spatial reference parameter does not use the same datum as the original data, we will need to supply a datum transformation, which is another optional parameter further down. We are going to see the spatial reference and the datum transformation in action in our search cursor section. We'll scroll back up. The explode to points optional parameter can take a boolean of true or false. If set to true, the search cursor returns a row for every vertex in the geometry. The next optional parameter is the SQL clause. The SQL clause is a tuple that contains two entries, a prefix clause and a postfix clause. The prefix clause can be none, distinct, and top. Now, top is only available in an enterprise geodatabase. The postfix clause supports none, order by, and group by. And we're going to see these in action in one of the videos in our search cursor section. Next up is the spatial filter. The spatial filter must be a geometry object. It is a geometry object used to spatially filter features. When this parameter is set, the cursor will limit the features returned based on the specified geometry and the spatial relationship value. By default, the spatial relationship is intersects. It is important to note that the spatial filter needs to be a geometry object. For the spatial relationship, if not set, the intersects is the default. But there are several other options. There's the envelope intersects, the index intersects, touches, overlaps, crosses, within, contains, and these are your basic geometry operations. We will see the spatial filter and the spatial relationship in action, where we use a polygon geometry from one data set to filter what is returned by the search cursor in another data set. The last optional parameter is the search order, and this is only available in an enterprise geodatabase. We have one property, and that is the fields property. The search cursor fields property returns a tuple containing the field names used by the cursor. The documentation states one method, that is the reset method, and this resets the cursor back to the first row. Now there is also a second method called next, which we will take a look at in this section. And we have some code examples of the search cursor at work. In this section, we are going to go through every parameter in fine detail to go far beyond the examples that are set here. In this video, we went through the Esri documentation for the search cursor. As of ArcGIS Pro 3.2, the search cursor has revamped with a couple of extra parameters, most notably the spatial filter and the spatial relationship parameters. In this video, we will use the search cursor on a layer in ArcGIS Pro and only use the required parameters. From the ArcPy cursors folder on your C drive, click into APRX, and we will double click on the ArcPy cursors.aprx to open it in ArcGIS Pro. The APRX will open with the cursors map open, and this map has 5 layers. We have points of interest, roads, buildings, other buildings, and land use. Up top, click into the Analysis tab, and on the left where it says Python, there's a drop down. Click the drop down and select Python window. Your Python interpreter will open, and this may take a moment or two while the Python interpreter initializes. When ready to go, we will click where it says Enter Python code here. We are going to use the search cursor to iterate through the rows in our Selbridge buildings layer and print the information to screen for each row. We start with the Python with statement, so with arcpy.da for the data access module, and we want the search cursor. You can type in or use the prompts. We can see that ArcGIS Pro has a nice list of the layers here to choose from. We can select Selbridge buildings. And ArcGIS Pro also displays the syntax for the search cursor. We've just entered the in table. If we add a comma, we can see it now highlights for field names and is prompting us to add in the asterisks for all fields. We'll click that. And to finish off our statement, we say as cursor and use a colon. We'll hit enter. We won't print out the attributes in our first run. Let's print the cursor to screen. Hit enter and enter. And this is to show that the cursor is a cursor object. It is a search cursor object. We'll click back into our Python input and we can press up to find previous statements entered. We'll remove our print cursor and we'll put in a for loop for row in our cursor. We want to print each row. We'll run the code. We'll scroll up a bit back to our Python statement. We can see that each row returned was a tuple of values. Here we have 1, and this 1 represents the object ID. If I right click on Selbridge buildings and open the attribute table, we can see here object ID of 1. Then we have shape polygon. This tuple here of points represents the centroid for the polygon. We see here we have St. Patrick's, and that is the attribute for the name field in our first row. We also have church. The rating is 0. Recommend is null, and Python represents null as none. We have the shape length, and we have the shape area. We can see our Selbridge buildings has 25 records, and all 25 have been printed to screen. If we take a look at the last one here, 25 is at index 0 in the tuple, and then our shape is index 1, our name is index 2, type is index 3, and so on. And we can use the index to access individual attributes as required. So let's take a look at that. Go back to our last statement. Instead of printing the whole row, we are just going to print row 2 and row 3, the elements at index 2 and 3 in our returned tuple. And as we just mentioned, element 2 or index 2 is the name and 3 is the type field. We'll run that and we can see we returned the name St. Patrick's and the type of church. And you're probably wondering why it didn't print it for all 25. And that is because there's currently a selection in our layer. The search cursor will honor any selections or definition queries set for a layer. If we clear the selection and run again, we can see it is printed out for all 25. In our previous examples, we have been using the asterisk to return all fields, but we can simply put in a field name just to return the information for one field. Here I've supplied the name field and we will just print the full row. And we can see all 25 are returned as a tuple with one entry. We could also access the first element in that row and we get a nice list of names printed to screen. Just to show what happens if we enter an index that doesn't exist in the information that is returned, we get an index error, tuple index out of range. We've supplied in row 1 where we're looking for the second element of the tuple returned, but we only have one field in there, so only one element is being returned. So there is no second element. If we are using more than one field to be returned, we need to use a list. So we'll set our list and we'll add in type and rating. And we'll print the entire row. We can see a tuple has been returned with the name, type and rating for all 25 of our rows. And again, we can pick and choose which ones we want to print. We'll say row 0 and row 2 and run. And this time we just got the name and the rating. In this video, we use the search cursor with the required parameters. When using the search cursor, each row returned is returned as a tuple. You can use the asterisk to return all fields, or you can use a single field or a list of fields to limit the information returned in each tuple. With each tuple returned, we saw that we could use indexing to access the information of interest. In this video, we will use the search cursor with the optional where clause to limit the rows returned by the search cursor. We are in the ArcPy Cursors APRX. You do not need to be following on from the previous video in order to perform the tasks in this lesson. We are going to use the search cursor on our Selbridge buildings layer, and we are going to use the where clause parameter to limit the rows returned. The where clause is an SQL statement where we define criteria in order to limit the number of rows returned by the search cursor. We'll begin with our with statement with ArcPy.da.searchCursor, and we're going to use our Selbridge buildings, and we will use the asterisk for all fields to be returned. Then we put the comma after our field names parameter. We see the where clause is now highlighted, and we are going to use double quotes, and then we are going to put in the name of a field. We will use type, and we're going to set that equal to retail. Now, because it is a string type field, a text field, we need to wrap the retail in single quotes. If it was a number, you omit the single quotes. We then finish off our Python statement with as cursor and hit enter. We now use the for loop for row in cursor. We will print out each attribute individually. So row 0, row 1, and row 2. And we'll run the code. No, that's not what I wanted to do. I wanted to print out the name, so row 2, and the type, row 3, and we'll run again. Now we can see that the output are all of type retail. Let's use the select by attributes tool, and we'll go with type is equal to retail and click apply, click OK, and we can see that 5 out of the 25 have been selected. And this is what our search cursor returned, our 5 retail records. We'll clear the selection. Let's use the where clause once more. This time we're going to set it where type equals retail and the rating is greater than 2. So you can see here there are no single quotes wrapped around the number. And we'll just return the name field. And we will print the name where it is retail and the rating is greater than 2. We'll run that now. And we can see we have the Abbey Lodge, Castown Inn and the Speaker Bar. 3 nice pubs in Selbridge. And let's do one more just to show another SQL statement. We'll return the name and rating. And we'll clear our where clause and we'll set it to be type in, and we use parentheses this time, and we'll go with retail and add in commercial. So now we are looking for any buildings that have a type of retail or commercial, and we're going to return the name and rating attribute. We'll print the name and the rating. And we can see the list that satisfies the criteria as defined by our SQL statement and used with our where clause. Just a little tip, if you ever need to know how to build an SQL statement, you can go into the select by attributes and use the drop downs here to create your statement. So we've just done where type includes the values retail and commercial. If you then click this SQL toggle, you can copy and paste this into your Python script or into the Python window below. Let's do that now. We'll toggle off SQL and we'll say where name includes the values Blake's Pharmacy, Castletown Inn, and let's go with St. Patrick's. We'll click the SQL toggle and we'll copy. We'll X out of that, select by attributes window. We'll go back down to our Python window. We'll click up and we are just going to replace the where clause in between the double quotes and paste in our SQL statement from our select by attributes window. And let's run the code. And we got our 3 returned: St. Patrick's, Casstown Inn and Blake's Pharmacy. In this video, we saw how we could use the optional where clause parameter to supply an SQL statement to limit the number of records returned. We supplied a handful of different SQL statements to our where clause, and we saw that we could build that SQL statement in ArcGIS Pro using the select by attributes tool and copy the SQL statement to our Python code. In this video, we will use the search cursor with field tokens to access system maintained fields and geometry. We are in the ArcPy Cursor's APRX. If you are following on from the previous video, all well and good, but you do not need to have followed this section up until now. You can jump straight in here and go through the workflow for this tutorial. We have our Python window open and the Selbridge buildings attribute table. In our first example, we are going to access the geometry for each entry in our Selbridge buildings attribute table. We begin with our with Python statement with arcpy.da.searchCursor. We choose our Selbridge buildings and we're going to access the name field, and we're going to use the shape at token to access the geometry object for each feature. So the shape at token accesses the geometry object for each feature. And we finish off our statement with as cursor and our colon and hit enter. We then use our for loop for row in our cursor. We will print row 0, which is the name field, and row 1, which is the geometry, the shape at token. We'll run our code. And we can see we got the name from the name field, and we also got this geometry object returned from the shape at token. In the resources for this video, there is a text file with the link to the geometry class in the Esri documents, where you can get more information on the geometry object. In our next example, we will take a brief look at some of the properties of our geometry object. We'll go again with a similar search cursor. This time we're going to use a where clause where the object ID is equal to 1. We're only going to look at one record, and we know that is going to be our St. Patrick's Church, where the object ID equals 1. We will print out the geometry type, so we'll go type and row 1, which is the geometry object, and we'll use the type property. We'll copy this print statement and enter and paste. And for our second one, we will put in area, which is the area property for our geometry object. We'll change the type to area, and we'll print once more. We will print the extent. And you guessed it, we use the extent property. I have also added a link to the extent class in the resources download, where you can find out more information about an extent object. We'll run our code. We can see we got type polygon, we got the area, which matches the area in our attribute table, and then we got the extent. So we have the x min, y min, x max, y max, and then we have not a number for our z min, z max, m min and m max, because they are not in play for this current geometry, as our feature class does not have z or m enabled. Let's take a look at the shape at area and shape at length tokens. We'll just update our previous search cursor. We'll add in shape at length and shape at area. And we'll continue just to use the first feature in our feature class. And for this run, we will print row 0, which is our name. We will print row 2, which is our area. And we'll print the perimeter, which is the length, which is our row 1. So let's take a look at that. We are printing the name from the first field. We are then using the shape at area token to print out our area, and the shape at length token to print out our perimeter. We'll run the code. We can see we have the attribute from our name field, the area from the shape area field, which is system maintained, and the perimeter, which is from the shape length field, which is also a system maintained field. We'll hit up and use our previous search cursor. We will remove the name and the shape at area. And we'll update our shape at length to be shape at WKT, which stands for well-known text. We'll again only access our first feature, and we will just print out the WKT. We'll run our code. And now we can see the well-known text representation for the geometry of our St. Patrick's Church. We'll go again, and this time we will use shape at JSON to get the GeoJSON representation for our geometry. Run the code. WKT and JSON are great when you are integrating with other applications. When you're using the ArcGIS API for Python, the JSON we have printed here enables you to update geometries in ArcGIS Online. We'll take a look at one more token, and that is the OID at token. The OID token accesses the OID field for the layer or feature class. Now the OID can be object ID, it can be FID, it could be named OID itself. It is the system maintained fields that ensures that each record in the table is unique. We will also add in the name field, and we will remove our where clause. We will print our OID field attribute and also the name attribute. We'll run our code, and we can see beside each name that is printed we have the object ID. I encourage you to use the OID at token when you wish to access the object ID or FID of any layer or feature class. It will enable the code to run without failure. Let me show you what I mean. If I hit up, let's say for one workflow it was FID, and this is how we constructed the code, and we went to run for a feature class that had object ID. We would get a failure that it cannot find the field FID. And if you had object ID in there and the OID field was FID, you would get cannot find field object ID. So the OID at token is very powerful for enabling automation across various file types. In this video, we looked at how we can use field tokens to access system maintained fields along with the geometry. We saw that the shape at token returned a geometry object, and from that geometry object we could interact with the properties of that geometry. We also saw that how the OID at token should be used as standard when accessing the object ID for any file type. In this video, we will assess the use of the spatial reference and the datum transformation parameters when using the search cursor. The spatial reference parameter is the spatial reference of the layer or feature class being supplied in the search cursor. When this parameter is supplied, the features will be projected or transformed from the input spatial reference to that set by the spatial reference parameter. When this parameter is unset, the spatial reference of the input feature class is used. The datum transformation parameter is used when the spatial reference parameter is set and the original feature class spatial reference and the spatial reference used in the parameter do not share the same datum. Therefore, an appropriate datum transformation needs to be specified. We are in the ArcPy Cursors APRX. If you've been following on from the previous video, that's great, but you do not need to have been following along in this section up until this point to follow this tutorial. We have our Python window open and our Selbridge Buildings attribute table. In our video on accessing field tokens, we accessed the JSON for our geometries. Let's do that once more. With ArcPy.da.SearchCursor, we select our Selbridge Buildings and we want to access the shape at JSON. We will only access this for our first feature, so we'll set our object ID equal to 1. And we finish off our line of code with as cursor and the colon and hit enter. We now use our for loop for row in cursor. And we're going to print row 0, which is the JSON representation of the geometry for our first feature. We'll run our code and we can see our output. In our next example, we are going to use the spatial reference parameter and supply in 4326, which is the code for WGS84. Click up, and if we go past our object ID equals 1 and put in a comma, we can see that spatial reference is now highlighted in our syntax. We will add in 4326 and run the code. And if we take a look, we can see that the output has been projected to WGS84 with lat and long rather than the original coordinates, which are in Irish Transverse Mercator 2157. The Irish Transverse Mercator is the latest projection system for Ireland, and it projects nicely back and forth between WGS 84. In the next example, I'm going to project using 29902, which is Irish National Grid. And we'll run the code. This means nothing at the moment. It looks like the search cursor has projected from ITM to Irish Grid, but unfortunately there is a datum transformation needed to project correctly between these two coordinate systems. We will use the ArcPy list transformations function to get a list of transformations that can be applied. The list transformation functions takes in two spatial reference objects, the original coordinate system and the coordinate system being projected into. We will set a variable called ITM, and this will equal ArcPy.spatialReference, and we'll supply in the spatial reference code, which is 2157 for Irish Transverse Mercator, and hit enter. We also create a variable for Irish Grid, and we'll set this equal to ArcPy.spatialReference, and we'll supply in 29902 and hit enter. And now we can call our ArcPy.list transformations, and we will supply in our ITM as our original and projecting to Irish Grid, and we'll hit enter. We can see a list of all the datum transformations that can be applied. We are going to use the first one here, so we will copy that, Control and C to copy, or you can right click and copy. So let's rerun the last search cursor that we ran, and we will add in our datum transformation parameter, and we'll set that equal to and paste in what we copied, and let's run our search cursor. I'll expand this window so we can see a bit better, and I'll move it down afterwards, and take a look at the differences in the coordinates. Our second run has been projected correctly, where our first run was not. I'll shrink this window back down in preparation for the next video. In this video, we saw the spatial reference parameter in action, that when we supplied a spatial reference, the search cursor automatically converted or projected from the data's original spatial reference into the spatial reference supplied. When the original spatial reference and the spatial reference supplied do not share the same datum, a datum transformation must be applied. In our example, we projected from Irish Transverse Mercator to Irish Grid and supplied a datum transformation in the datum transformation parameter. We saw that we could use the ArcPy list transformations to list the possible datum transformations that could be applied to our data. In this video, we are going to take a look at the optional explode to points parameter available with the search cursor. If the explode to points parameter is set to true, each vertex in the geometry for the feature is accessed individually. For example, take a rectangle polygon. You will have top left, top right, bottom left, and then the closing top left vertex. A feature represented by this rectangle will be represented as 5 rows when the explode to points parameter is set to true. We are in our ArcPy cursors APRX, and if you are continuing on from the previous video, all good, but if not, do not worry, you do not have to have completed the previous videos in this section up to this point. You can follow this tutorial from start to finish. We have the Python window open along with our Selbridge buildings attribute table. Let's build a search cursor statement. We begin with arcpy.da.searchCursor, and we select our Selbridge buildings. We'll provide a list of field names. We'll use the OID at token, our name field, and our type field. And we'll set the explode to points parameter to equal true. finish off our statement with as cursor and hit enter. We now kick into our for loop for row in cursor, and we are going to print each element: row 0, row 1, and row 2. Row 0 is our OID, row 1 is our name, and row 2 is our type. And let's try run this code. Nothing seems to have exploded there, does it? We can see all 25 of our features printed in order from 1 to 25. But this is not what we expected. In order to use the explode to points, you need to add in the shape at token. So let's add that in now. And let's print that element from our list out. So we'll add in row 3 and we will rerun. And now we get what we are looking for. The polygon geometry for every feature has been exploded, and each vertex is represented by a geometry object, which we will see in the next example is a point. Let's rerun the previous code with one minor tweak. We will put in row3.type. This will print the type of the geometry object. It is the type property for the geometry object returned. And we can see that they are all points. Let's run one more example. This time we will limit what is returned to our first feature. So we'll set object ID to equal 1. And we'll print out row3 dot first point dot x. This will give the x value for each point that has been exploded from the original polygon. And then we'll also add in row3 dot first point dot y to get the y coordinate. Let's run that and see what is returned. So for each vertex in the St. Patrick's geometry, which is object ID 1, and we have the type of church, we have got the x and y value for each point. Each x and y value represents a vertex from the original polygon geometry. You might be thinking, when on earth will I ever need such an option to explode the polygons to points? Later on in this course, we are going to create a feature vertices to points tool, which will be a custom tool in ArcGIS Pro. This tool is available on an advanced license, but we're going to use what we've learned here with the explode to points parameter with the SearchCursor and ArcPy to recreate this tool for use on a basic license. In this video, we explored the use of the optional explode to points parameter with the SearchCursor. We now know that you need to supply the shape at token in order for the explode to points to function as intended. Each vertex in the geometry is represented by a point geometry object, and we saw that we could access the properties for each point individually. In this video, we will look at the optional SQL clause that you can use with the SearchCursor. The SQL clause is a tuple that contains an SQL prefix and a postfix clause. An SQL prefix clause can be none, distinct, and top, and the SQL postfix clause can be none, order by, or group by. We are in our ArcPy Cursor's APRX. You do not have to follow the previous videos in this section to follow along with this tutorial. We have our Python window open along with the Selbridge Buildings attribute table. In our first example, we are going to use the SQL clause with a prefix of distinct and a postfix of none, and we're going to return the unique values for our type field. We'll begin with our with statement with ArcPy.da.SearchCursor. When we select our Selbridge Buildings, we are only interested in the type field, and we're going to set our SQL clause optional parameter to equal a tuple that contains the word distinct, followed by a space and the name of the field that we wish to get the distinct values for, the unique values for, which is type. We know that the SQL clause is a tuple, so we'll add in none for the postfix. We need to add in a closing parentheses and finish off with as cursor, and we'll hit enter. We're now into our for loop for row in cursor. We will print row 0, the first element from the attribute returned, which is only our type field. So we know our type field has values that are reused throughout the features, such as retail and commercial, and we are only going to get the unique values printed to screen. Let's run the code. We see we have 5 unique values produced from the distinct clause. Let's get our search cursor back up, and instead of type we're going to use the name field, and we'll set our prefix clause to be top 5. Now realistically they should only return the top 5 rows, but I'm going to run this and show you the error that we get. We get a runtime error that an invalid SQL statement was used. And we were actually expecting this error. The documentation states that the top prefix clause is only supported by SQL Server databases. So it will not work when our data is outside of an SQL Server database. Let's switch things up and use the postfix clause. We will stick with our name field. We'll change top 5 here to none for the prefix, and for our postfix we're going to use order by and our name field. And what do we expect to be printed out here? We expect for all 25 of our records that the name field attribute will be printed out in alphabetical order. We'll run the code. We got an invalid syntax error. Can you point out what was wrong? Our postfix clause needed to be wrapped in string quotes. Now when we run, we'll get all our names printed out in alphabetical order. And of course we can reverse that and put a DEC for descending order in our clause. We'll rerun, and we can see they are now in descending order, in reverse alphabetical order. For our last example, we will use the group by clause for the postfix clause. We will change our name field to our type field, and we will group by our type field. Don't need descending. This is going to produce the same results as our distinct prefix clause. We are going to get unique values from our type field. We'll run the code, and you can see we have our 5 unique values. Let's do one more example. Let's add in an extra field. We will put in our ratings field. We'll still group by type, and we will add in row 1 and run our code. We can see we got an error. Let's try add in our group by type and rating, and run again. And we get all the different groups for our type and rating. So we needed to add in both fields that were supplied to the search cursor to our group by clause. Unfortunately, there is no way that we can add in a group by and an order by clause. It would be nice to have seen our output ordered. We will, however, be taking a look at how we can return sorted data later on in this section when we use the search cursor with list comprehension. In this video, we use the optional SQL clause with our search cursor. We saw that the SQL clause is a tuple that can contain an SQL prefix and an SQL postfix clause. We used the distinct prefix clause, and we saw that the top is only supported by enterprise datasets that sit in an SQL Server database. We used the order by postfix clause to order the information returned in alphabetical order and in reverse alphabetical order. And finally, we used the group by function where we saw we needed to supply in both our fields that were used in the SearchCursor fields parameter, and that by supplying one it returned an error. In this video we will use the optional spatial filter parameter for the SearchCursor. The spatial filter parameter, when set, must be a geometry object. When the spatial filter parameter is set, the SearchCursor will limit the features returned based on the supplied geometry object and the spatial relationship parameter value. So we also need to supply a spatial relationship parameter when we use the spatial filter parameter. Here we are in our ArcPy Cursor's APRX. You do not need to have followed the previous videos in this section to follow this tutorial. We have open our Python window and our Cellbridge Buildings attribute table. We will also open the Cellbridge Land Use attribute table, so right click on the layer and select Attribute Table. We have 5 features in our Cellbridge Land Use feature class. The polygons represented in this feature class are multi-part. If I scroll down to Residential and select, we can see that multiple polygons have been selected in the map. We are going to get the geometry object from our residential record and use this for the spatial filter parameter in our SearchCursor. I'll clear the selection and head down to our Python window. We start with arcpy.da.searchcursor and we select our Cellbridge Land Use layer, and we are interested in the shape at token. We want the geometry object for our residential record. We'll set a where clause just to return the residential row. So we set where f class is equal to residential. We then finish off our statement with as cursor and hit enter. We use a for loop for row in cursor. We know only one record is going to be returned. We'll create a variable called filter_geom and we'll set this equal to row 0. The filter geom variable will represent our geometry object. Let's print that filter geom to screen and make sure it is a geometry object. We'll run our code and we can see we were returned the geometry object. We'll switch our attribute table into our Cellbridge Buildings and go back down to our Python window, and we'll perform another SearchCursor with arcpy.da.searchCursor. This time we want to use our Cellbridge Buildings. We're interested in the name and type fields, and we will set our spatial filter parameter, which is an optional parameter, and we'll set this to equal our filter geom. We also need to use the spatial relationship parameter, and we want it where our Cellbridge Buildings intersect the retail geometry. So we will use intersects. Intersects is the default, so if we did not set the spatial relationship, intersect would be used. We finish off our statement with as cursor and hit enter. We then use the for loop for row in cursor, and we will print out row element 0 and row element 1. Row 0 is our name field and row 1 is type. We'll run the code and we see we got 4 rows returned for Riverview Apartments with a type of residential. Let's take this workflow a little further. Let's create a variable called OID list and we'll set it to be an empty list. We'll then use our SearchCursor. We'll use similar to the previous, but we're going to change name and type fields to OID at. We are using the OID token to only return the object ID values. We'll leave our spatial filter as is with the filter geom, which represents the residential areas, and we'll leave the spatial relationship as intersects. For each iteration, we are going to append in the object ID to our OID list. Run the code. Now we'll print our OID list to screen. We can see we have 8, 21, 22 and 23. These will represent the 4 polygons for the Riverview apartments. We'll get our Cellbridge buildings layer as a layer object. First we need to access our APRX. We'll create a variable called APRX and set that equal to arcpy.mp.arcgis project, and we'll create an ArcGIS project object by supplying in our current value, which means that the APRX will represent our open APRX that we are working in. We'll create a variable called m for a map, set that equal to aprx.listMaps, and the map we are interested in is our cursors map. Now the list map always returns a list, and we are only interested in the first element of that list. Oops, that should have been list maps. Hit enter again. Now if I click m.name, we have our cursors map. We want to access our Cellbridge buildings layer. We'll create a variable called buildings_layer, and we'll set that equal to m.listLayers. Got it right this time. And we'll supply in our Cellbridge buildings with a B, and we're only interested in the first element of the list returned by the list layers function. We'll hit enter and we will print buildings layer to screen. We can see it is a layer object, and we can use the layer object name property to get the name of the layer. We can see it is indeed our Cellbridge buildings. We'll take our layer object and we will use the set selection function and supply in our OID list. Now before hitting enter, I want to zoom in on the map up here. Here we have our 4 Riverview apartments. They intersect the retail geometry, the retail polygon, and these are going to be selected when we run our piece of code. We'll hit enter and we can see the 4 of them have been selected. In our attribute table, we can see 4 of 25 selected. And if we click into the show selected records, we have our 4 records present. I'll click back into the full table and we can remove the selection by using the set selection set function and supplying in no parameters. And we can see our selection has been removed. In this video, we use the optional spatial filter parameter with our search cursor. We use the search cursor to get a geometry object from a polygon layer that represented land use, and we used that geometry object as our spatial filter, where we use a second search cursor to find features from our buildings layer that intersected the geometry object returned from our first search cursor. We added a little extra to our workflow by getting the OIDs of the buildings that intersected our geometry object and used the layer object set selection set function to select the features that intersected. In this video, we will take a look at the only property available with the search cursor, and that is the fields property. The fields property will allow us to access the field names through the cursor. We are in our ArcPy Cursor's APRX. You do not have to have followed any previous videos in this section in order to follow this tutorial. We have our Python window open and our Cellbridge buildings and land use attribute tables open. I'm going to close the land use attribute table. We'll head down to our Python window and we'll begin with arcpy.da.searchCursor. We select our Cellbridge buildings layer. And we will use the asterisk. We want to return all fields. We'll finish off with as cursor and hit enter. We will use a print statement and we will print cursor dot fields. We'll run the code. We can see we were returned a tuple containing the field names from the Cellbridge Buildings layer. In an upcoming video, we are going to take a look at using Python list comprehension and search cursors to return information. But here I'm going to give you a little teaser. Let's set a variable called fields list, and we'll set that equal to a list. For our list comprehension, we will use field for field in ArcPy.da.searchCursor. We want our Cellbridge Buildings. We'll again use the asterisk for all fields to be returned. And after our search cursor, we'll hit dot and put in the property fields. So for each field in our ArcPy.da.searchCursor fields property, we want to create a list that contains each field name. And we're applying this list to a variable called fields list. We'll run our line of code. And if we print fields list to screen, we have a list of our field names. It is generally more efficient than using a for loop. As an added bonus, let's look at another way that we can get a list of all the field names for a layer. We'll overwrite our fields list variable, and again we will use list comprehension. This time we are going to use the ArcPy list fields function. For field in ArcPy.list fields, and we want to add in our Cellbridge Buildings layer. Now the ArcPy.list fields function returns a list of field objects, and we want the name property from that field object. So we want field.name to be returned for our list. We'll run our code. And we'll print the field list variable, and we can see once more our list of field names returned from our layer this time rather than the search cursor. For completeness, let's run the search cursor once more, and this time we will put in a selection of field names. We'll use our name field and our type field, and we'll run to print the cursor fields property to screen. And we can see our name and type were the only two fields returned. So the cursor fields property honors the fields that were entered into the field names parameter for the search cursor. In this video, we saw the search cursor fields property in action. The fields property returns any field name that is used in the field names parameter for the search cursor. We saw how efficient and neat list comprehension is in Python, so I hope you're getting excited for learning more about those in a future video towards the end of this section. In this video, we will take a look at the reset method available with a search cursor. The reset method resets the cursor back to the first row. We are in the ArcPy Cursor's APRX, and you do not have to have followed the previous videos in this section to follow along with this tutorial. We have our Python window open and our Cellbridge Buildings attribute table. Let's take a look how the reset method for the search cursor works. We begin with ArcPy.da.searchCursor, and we'll use our Cellbridge Buildings layer. We'll supply in two fields for the field names parameter as a list. We will use our name field and the type field. And we finish off this line of code with as cursor and hit enter. We go with our for loop for row in cursor. So this will iterate through each row in our attribute table for our Cellbridge Buildings. We're going to use an if statement. If row 1, which is our type field, equals retail, we will print our values to screen, row 1 and row 0. So we'll print the type and the name to screen. We'll then step back out of the if statement and out of the for loop. Let's print resetting cursor to screen when we hit this point. Hit enter. And we're going to call our cursor object dot and the reset method. We'll hit enter. Let's recap on what is happening. We are using a for cursor to iterate through each feature in our layer. If the type field has an attribute of retail, we are going to print the type and the name attributes to screen. So we only expect to see features printed with a type of retail. We're then going to reset our cursor. This puts it back up to the first row. We will now run a second for loop for row in cursor. So we're still using the same cursor object. It has just been reset. If row 1 equals, and we'll go with commercial, we will print the information. Let's run our code. We can see that all our retail buildings were printed first. We then reset the cursor and we went through the cursor a second time, starting at the first row again, and we printed out any feature that had a type of commercial. In this short video, we saw the reset method for the search cursor in action. We iterated through every row in our Selbridge buildings layer, and we printed information to screen if it met certain criteria. We then used the reset method to reset the search cursor back to the first row, where we iterated once more through every record in our buildings layer to print out a separate set of information if another criteria was met. We will see more of the reset method in the next video. In this video, we will use the next method available with a search cursor to move through each row in the cursor one by one. We have our ArcPy Cursor's APRX open. While you do not have to have followed any of the previous videos in this section up to this point to be able to follow this tutorial, we will be using the reset method from the previous video, so it may be worthwhile checking that out first, but not essential. We have our Python window open along with the Selbridge buildings attribute table. So far we have been using the search cursor with the with Python statement. The with statement is an efficient way of closing the cursor. Once the code within the with statement has completed, our cursor is automatically closed. We're not going to use the with statement here. We'll create a variable called cursor and we'll set this equal to arcpy.da.searchCursor. We'll choose our Selbridge buildings. Let's supply in two fields. We'll use the OID at token to retrieve the object IDs, and we will also get the name attribute. We'll run this line of code, and if we print our cursor to screen, we can see we have a search cursor object. Now look what happens when I call the cursor object dot next method. We'll hit enter, and we will return to the first row from the cursor. Let's go again. We got the second row, and we could keep going until we get through all 25. But what happens if we went too far? We could call the cursor dot reset method and run. Now when we call our next method, we are back to the first row. I know what you're thinking. What happens if we call next when there is no next row? Well, let's find out. Let's use the search cursor to return just one row. We'll add in a where clause where the name is equal to Selbridge library, and we'll create our cursor object. We'll call the cursor.next method. We have our Selbridge library. It should be the only one returned. We'll go again with next, and we get an error, a stop iteration. Now what happens if we reset? And we'll go next, So even though we hit the error, we can still call the reset and go back to the first row. Now, if you're performing this in a standalone script, you would have to handle that stop iteration error gracefully. The cursor will remain open until we delete it. So let's delete our cursor. Now if we call cursor.next, we have no variable called cursor. In this video, we saw an alternate way to use the search cursor rather than all the previous videos where we use the with Python statement. We used the ArcPy search cursor to create a cursor object. We then saw that we could use the search cursor next method to move through each row returned one by one. In this video, we will use list comprehension with the search cursor to efficiently extract information from the search cursor. We are in the ArcPy Cursor's APRX. While you do not have to perform tasks from the previous videos in this section, the knowledge gained will help to understand this tutorial. We saw list comprehension in action back in the fields property video, and we're going to dive a bit more into list comprehensions with search cursors in this video. We have our Python window open and the Selbridge buildings attribute table. For our first example, we are going to get a list of all the attributes in the name field. Let's see how that would look without list comprehension first. We'll create a variable called buildings list and we'll set this to be an empty list. We will then use our ArcPy.da.SearchCursor and supply in the Selbridge buildings as our in table. We are only interested in the name field, and we'll finish off our statement with as cursor and the colon and hit enter. We now need a for loop for row in cursor. We want to append to our buildings list, and we want to append in row 0, which is the name field attribute. We'll run our code and we'll print the buildings list to screen. We have all 25 names in there. We can go length buildings list and you can see we have all 25. So that took us 4 lines of code. With list comprehension, we are going to do it in one line. Let's create a variable called buildings list underscore LC for list comprehension. Set this to be a list, and in this list we're going to state for row in ArcPy.da.SearchCursor, and we supply in our Selbridge buildings and our name field. And if we go back to the start of our statement, we are looking for row 0 to be returned as the elements of the list. Row 0 will be the name attribute. We'll run our line of code and we will print the buildings list LC to screen. And we got the same return as our previous example with all 25 names. I want you to cast your mind back to the SQL clause video if you watched it. In that video, we used the SQL clause postfix group by, and we grouped by rating and type. Now, at the end of that video, I posed that it would be great if we could also order what was returned, but unfortunately, we could not add in the order by and the group by into the postfix clause together. So let's take a look here how we can overcome this by using list comprehension. Let's overwrite our buildings list variable and we'll set this to equal a list. List comprehension always returns a list. In this example, we are going to return a list of lists. Each list inside our list will contain 2 elements, the rating attribute and the type attribute. Our statement will read for row in ArcPy.da.SearchCursor. We'll add in our Selbridge buildings and we're interested in the rating and type field. We'll set our SQL clause to equal a tuple. Our prefix is none and our postfix is group by rating and type. We now go back to the beginning of our statement. We'll add in row 0, comma, row 1, and wrap these in square brackets. This part here represents the lists that will be returned inside of our list returned from the list comprehension. Now we do want this sorted, so we'll use the sorted built-in function. So we wrap everything in the sorted parentheses, and we need to tell the sorted function how we want it sorted. So after our list comprehension, we'll put in a comma. We'll set key equal lambda, and our lambda function will be to return our list sorted by the second element first and then our first element. And this should give us our ratings in order and grouped by the type attribute. Let's run our code. I had a feeling I was going to get an error there with all those different square brackets and parentheses. So where is the culprit? Here we go. It can be a bit of an annoyance using the Python window. If I show you here, I put in an opening and then closing. It doesn't add in the second closing, it just overwrites it. So we rectify and we'll run again. No error this time. Let's do a for loop for group in buildings list. Print the group. Oh, look at that. Perfect. We have our church, we have all our commercials, and we have public, residential, retail, all grouped nicely. Let's go one more. Let's look for retail buildings. We'll set that to equal a list. We'll set our statement for row in ArcPy.da.SearchCursor, and we'll select Savage Buildings. And we're only interested in returning the object ID. So let's use the OID @ token. And we'll set our where clause where type equals retail. And we only want the OID returned, so row 0. So we should get a list of OIDs where the type attribute is retail. Let's run that code. And we will print retail buildings to screen. And we have 5 OIDs in our list. Let's get an ArcGIS project object. We'll call it APRX. And we need to use arcpy.mp.arcgis project and supply in the current string and hit enter. We now have access to our current open APRX. We'll create a variable called m to stand for map. We'll set that equal to APRX. So from our ArcGIS project object, we are going to use the list maps function and supply in our cursor's map name. List maps always returns a list, so we want the first element of that list. If we print m.name, we can see we have our cursor's map. From our map, we want to get our Savage Buildings layer. So we'll set our buildings layer to equal m.list layers, and we'll supply in our Selbridge Buildings layer name. Again, list layers always returns a list, and we only want the first element, and we can check what we returned by printing building layers to screen. We see it is a layer object, and we can also print the name property of the layer object, and we get Savage Buildings. Let's take another look at our retail buildings. We have 5 object IDs. Let's access our buildings layer, and we want to use the set selection set function for a layer object and supply in our OID list, which is our retail buildings. Before running this, we'll just go up to the map and we'll zoom out a bit. and we should see all 5 of our retail buildings selected in the map. We should also see 5 out of 25 selected in our attribute table. So let's run the code, and we can see 5 out of 25 selected, and we can see the 5 selections in the map. In our attribute table, we can click into show selected records, and we can see the 5, the Abbey Lodge, Michelangelo's, Castletown Inn, the Speaker Bar, and the Duck. Go back down to our code, and we'll show how we can clear the selection. We use the layer object set selection set again, but we do not supply in any parameter. Hit enter, and we can see the selection disappear. In this video, we witnessed the power and efficiency of using list comprehension with search cursors. I encourage you to use list comprehension as much as you can with search cursors and the other cursors until they become second nature in your workflows. They really add efficiency and code readability to your scripts. In this video, we will combine the use of the search cursor with Python set comprehension. Set comprehension enables us to return a unique set of values for a field in ArcGIS Pro. We are in our ArcPy Cursor's APRX. You do not have to have followed any of this section up to this point to be able to follow through with this tutorial. However, the knowledge gained throughout the previous videos would be beneficial. We have our Python window open along with our Selbridge Buildings layer attribute table. We are going to get a set of unique values from our type field. We have 25 features in our Selbridge Buildings layer, and the same building type can be used multiple times. Here we see commercial and residential. Let's get a unique set of values. We'll create a variable called building types, and we'll set this to equal a set of closed curly braces, which currently represents an empty set. Inside the curly braces, we'll add our statement for row in ArcPy.da.SearchCursor. We select the Selbridge Buildings, and we're only interested in the type field. We go back to the start of our statement, and we add in row 0, which represents the type attribute. So our statement reads row 0 for row in ArcPy.da.SearchCursor, where the in table is Selbridge Buildings and the field names supplied is type. If you followed along in the previous video, we saw list comprehension at work, and I'm going to run this as list comprehension first. So I'll remove the curly braces and put in our square brackets for our list, and we'll run the code, and we'll print building types to screen. We can see all 25 values were returned for the type field, including duplicates. Let's put back in our curly braces. We now have set comprehension, and the set cannot contain duplicates. Let's run our line of code and reprint building types, and now we only have unique values. We can use the built-in Python type function and add in our building types, and we can see it is a set. This means that we can perform any set type operations on it: add, clear, copy, difference, intersection, and so on. I'll clear this here. We can run again, and we can cast it to a list if we wish to get a list of unique values and have a list type returned. Now we try type buildings type. We get a class types generic alias, which I've never seen because I've gone wrong. I needed to wrap the list in parentheses. And we get types again. Now we have a list type, and we can print our building types to screen. It is now a list, and we can perform any list actions such as append, clear, count, insert, remove, and so on. We can go one step further, and we can wrap our list in a sorted inbuilt function. And now when we print the building types to screen, we can see they are in alphabetical order. In this video, we saw search cursors in action with set comprehension. Set comprehension enabled us to return unique values for a field. In this video, we will combine the use of the search cursor with a Python dictionary comprehension. Using dictionary comprehension with the search cursor is a fantastic way to fetch and store data in a variable. We are in the ArcPy Cursor's APRX. You do not have to have completed any videos in this section up until this point in order to be able to follow along with this tutorial. However, the knowledge built up from the previous videos is beneficial. We have our Python window open and our Selbridge buildings attribute table. We are going to use the search cursor with Python dictionary comprehension to retrieve data. Let's create a variable called buildings, and we'll set this to equal an empty set of curly braces. We saw in the previous video that this can be used for set comprehension, and here we're going to see the difference of how to perform dictionary comprehension. We'll add in our statement for row in arcpy.da.searchCursor, and we select Selbridge buildings, and let's supply in a list of field names. We will use the OID @ token to access the object ID, and we will access the name field. We go back to the beginning of our statement. We're going to add in row 0, which represents our OID. If you ran this code in its current state, it would return a set of all the object IDs. Let's take a look at that. We'll run the line of code, and if we go type buildings, we can see it is a set. Let's go back to our code. After row 0, we're going to put in a colon and add in row 1, which represents our name attribute. This part here with row 0 and the colon row 1 now makes this dictionary comprehension. Let's run this line of code and take a look. We'll get the type of the object once more, and we can see it is now a dictionary. Let's print buildings to screen, and we can see our dictionary printed. We have object ID of 1 for St. Patrick's, 2 for the Abbey Lodge, and so on. And we can also do a for loop for key value in buildings dot item. We will print the key and the value. This will go through each entry in our dictionary and print the object ID as the key and the name as the value. We'll run our code. Dot items. And we can see all 25 of our features printed to screen with object ID and the name attribute. Let's add in an extra field. We will add in our type field. And instead of our value, we are going to have a list, and the list will contain our name and our type. We expect the dictionary returned to have a key of our object ID and a value that is a list containing 2 elements, the name and the type attributes. We'll run our code, and let's rerun our for loop. And we can see we now have our object ID and our list of attributes. Let's add in a couple more fields. We will add in our rating field and our recommend field. And maybe you needed to add in a few more fields. We don't really want to have to type out row 3, row 4, row 5, row 6, etc. So let's use slicing. We'll remove our value part, and we will add in row 1 and a colon. So for each row, we are going to get the second field onwards: name, type, rating, and recommend. Let's run the code, and let's rerun our for loop. And we can see we nice and neatly got key as object ID and the value as a tuple containing our attributes. Often when we use geoprocessing tools, the resulting output feature class will contain a field called original ID or original FID, and using dictionary comprehension with the search cursor can be a fantastic way to link data back to original datasets and perform various data workflows based on this by implementing the insert or the update cursor that we will also be going through in this course. In this video, we saw how we can use the search cursor with the Python dictionary comprehension. Dictionary comprehension is a great way to store attribute information within your ArcPy scripts. In this video, we will dive a bit more into retrieving unique values for a field using the search cursor and list comprehension. Everywhere I have worked and deployed ArcPy solutions, getting unique values was always a requirement for a workflow at some stage during a project. I have no doubt that knowing how to get unique values will be beneficial to you. Open up the uniquevalues.py script from the other folder in your Python scripts. We'll first import ArcPy. We're going to use two of our original feature classes, our Selbridge Roads feature class and our Selbridge Buildings feature class. For our Selbridge Roads, we are interested in getting the unique values from the name field, and for our Selbridge Buildings, we are interested in the recommend field. The name field is a text field and recommend is a numerical field. Let's get started. Let's first return unique values as a set that we have seen previously. For each row in our arcpy.da.searchCursor, we set our inTable to be our feature class, which for this run is our Selbridge Roads, and our field names will be a single field, which is our name field. For each row, we are only interested in the first element, which is our only element, our name attribute. We wrap all this in curly braces and we should be returned a set. Now if we scroll down, for each run, we are going to print out the type of the unique values variable and also the unique values themselves. Let's run the script. And we can see we were returned a set, and our set is an unordered list of our unique road names. We can see we have an empty string in there. Not quite an empty string, it is a space. Let's now run that for the recommend field from our Selbridge Buildings. We got returned a set and our values are 1, 2, 3 and none. So there is a null value in our recommend field. Let's comment out our first example and reset our Selbridge Roads to be the feature class of interest. And in our second example, we are going to call the sorted method, which is an inbuilt function with Python, and supply our set comprehension as the parameter. Let's run the script. We can see that by calling the sorted method, our set was automatically cast to a list. And we can see that our values have been sorted in alphabetical order. In a previous example, in the set comprehension video, we explicitly cast this to a list by adding list in here and putting in the parentheses. Just to note that you do not need to cast it as a list, that sorted will do that for you. I'll remove casting to list. Let's switch to our Selbridge Buildings feature class. And we will run the same. Now remember, there is a null in there and a none value. And we get an error. We get a type error. Basically, this is telling us that the sorted function cannot sort when there is a none type value in there. That the sort is not supported between instances of none type and int. Let's continue. We'll comment out our second example, and again we will reinstate our Selbridge Roads feature class as the main feature class to use, and we'll get a list of unique values, this time rather than a set, Comment out and let's run. You can see we got our list and that the list returned is unsorted. We can also do the same for our Cellbridge Buildings feature class using the numerical field. We can see we got our list, and it's just fortunate that we got them in ascending orders for the number and none at the end. I'll comment out that example. This one here we've already seen. I will not rerun. This is where we have used the list class to cast the set as a list before sorting, but we know that the sorted function automatically casts it to a list. I'll comment this out and we'll move on to the next example where we're going to use the SQL clause distinct to return unique values. We currently have our feature class set as our Cellbridge Buildings and the recommend field. Here we're updating our statement. For each row in our search cursor, our in table is our feature class, our field names is our field name, which in this instance is recommend. And we're using the SQL clause parameter where our prefix clause is distinct and our postfix clause is none. We are using list comprehension to return distinct values for our recommend field. Let's run the script. We will return the list and we can see we got our distinct values and they are different from the last time we ran the list comprehension. Let's run again, but this time we want to sort the list. I know, I can hear you. Last time we tried to do this with a none value, we got a type value error that we could not sort when we had a none value and an integer. Let's overcome that with these lines of code here. If our none value is found in our unique values list, which it will be, let's remove the none value, sort our list while our none value has been taken out, and then insert the none value as the first element in our list. You could get a bit more fancier here with ascending and descending lists, but I'll leave that as a little exercise for yourself to contend with. Let's run our code. And we can see we got our sorted list with none as our first element and then 1, 2, 3 ascending. This video focused on getting unique values for a numerical field and a text field using the search cursor along with list and set comprehension. For the most part it is fairly straightforward, but we did see we got a type error when we tried to call the sorted method on a list or set that contained a none value, and a none value represents a null attribute from our attribute table. Getting unique values from a field is a common workflow I have performed on many projects, and I am very sure you will need it at some stage too.